Hi, I'm Alan Mishler. This talk is about post-processing risk assessment instruments to satisfy counterfactual equalized odds, and this is work with Edward Kennedy and Alex Chouldechova at Carnegie Mellon. The goal of this work is to post-process a possibly unfair risk assessment instrument, or RAI, to render it fair. By risk assessment instrument, we mean a predictor that's used to estimate the risk of an adverse outcome absent some intervention. For example, in healthcare, an RAI might ask, what's the risk that a patient will develop complications if not given some treatment? In criminal justice, it might ask, what's the risk that a defendant will recidivate if released pre-trial? A decision maker with access to this so-called risk score may choose to take it into account in their decision making. So RAIs are used in domains where we may not want to fully automate decision making for moral, legal, or practical reasons, and that distinguishes the task of developing risk assessment instruments from, say, optimal policy learning. So with a risk assessment instrument, the final treatment decision always rests with the person. As with many other applications of machine learning, there's broad concern about whether RAIs are fair or biased. This includes lots of domains like credit scoring, recidivism prediction, and healthcare. So to discuss error rates in risk assessment instruments and to talk about fairness in general, we first have to define what RAIs actually predict. Here's our problem setting and notation. We have a binary sensitive feature A, additional covariates X, such as demographic info or medical history, an existing binary risk assessment instrument S, which will be the target of post-processing, a binary decision D, such as whether or not to hospitalize a patient, and a binary outcome Y, such as patient death. Y0 is the outcome that would occur if, possibly contrary to FAccT, the decision were set to 0. In risk assessment settings, there's generally a baseline decision D equals 0, like the decision not to hospitalize a patient or the decision to release someone pre-trial. So the RAI targets the probability that an adverse outcome would occur under that default course of action. If the estimated risk is high, a decision maker might decide to adopt an intervention, such as hospitalizing a patient or detaining a defendant pre-trial. Of course, there's no consensus about how to quantify fairness, but arguably the most popular fairness criteria restrict the distribution of the sensitive feature A, the predictor S, and the observable outcome Y. Since we've argued that RAIs are naturally interested in the potential outcome Y0, we'll instead target counterfactual versions of these criteria. In particular, in this work, we'll focus on counterfactual equalized odds, which requires the predictor to be independent of the sensitive feature conditional on Y0. And note here that we're considering the counterfactual of the decision D, which distinguishes these criteria from other causally motivated fairness notions that consider counterfactuals of the sensitive feature A. So our Y0 asks, what would happen if a patient were not to be hospitalized, as opposed to say, what would the algorithm have predicted if the patient had been of a different race their whole life? Equalized odds is the same as insisting that the false positive and false negative rates be equal for the levels of the sensitive feature, say for Black patients and white patients. And the counterfactual version, again, just substitutes Y0 for Y. So in our hospital example, a counterfactual false positive occurs when a patient who does not require hospitalization is incorrectly labeled high risk. A counterfactual false negative occurs when a patient who does require hospitalization is incorrectly labeled low risk. Notice that with the observable outcome, a false positive occurs if a patient is labeled high risk, gets hospitalized, and survives, even if hospitalization in fact saved their life. That doesn't seem like a case that we'd actually want to label an error, since the RAI appropriately identified that patient as high risk. That's why we contend that we care about Y0 instead of Y. In fact, if we focus on satisfying observable equalized odds, which is the usual definition, we're likely to end up with unfair risk assessment instruments. Here we have two hypothetical predictors, one satisfying the usual notion of equalized odds on the left, and the other satisfying the counterfactual version. On the x-axis, we have the sensitive feature A, and on the y-axis, the counterfactual true positive rate. The true positive rate is, say, the proportion of patients who require hospitalization who are correctly identified as such. Require hospitalization means they'll have an adverse outcome if not hospitalized. For the counterfactual equalized odds predictor, these rates are equal by design for, again, say, Black versus white patients. But for the observational equalized odds predictor, these rates can be arbitrarily different. Now, why post-processing? There are obviously many approaches to satisfying fairness, but post-processing is appealing in the risk assessment setting because it can be implemented on top of an existing predictor. Many of the RAIs in actual use today were developed by for-profit companies, so their models are proprietary. That means researchers have no access to the internals, so their outputs can only be changed after they're generated. Another appealing aspect of post-processing is that if the input predictor has decent performance, then we may not require many additional inputs at runtime. That is, rather than training a new predictor from scratch, which may be expensive and require lots of variables, we utilize what the existing predictor has learned, and we just adjust the output to satisfy fairness. The flip side to that, of course, is that we're limited by the performance of the input predictor. If it's bad, we will likely get a bad post-process predictor. Now we'll define the post-process predictor. So as a reminder, here are our variables. S is the previously trained predictor that we're going to post-process. So we'll call S the input predictor. Our post-processing strategy is the same strategy used by Hart et al. Namely, we're going to flip S, the input predictor, with probability that depends on the sensitive feature and the value of S itself. So the class of predictors that we're considering are randomized classifiers where the randomness comes from A and S. And since A and S are both binary, this means we have a four-dimensional parameter representing these four probabilities. So that's the class of predictors we're considering. To define the optimal predictor within that class, we need to define loss optimality and fairness. For the loss, we're going to consider weighted classification error with weights W plus for the false positives and W minus for the false negatives, both chosen by the user. And note that we're using the term loss for the expected error rather than risk to avoid conflating statistical risk with the risk of adverse outcomes. The fairness criterion here is approximate counterfactual equalized odds, and to define that, we'll let delta plus denote the difference in counterfactual false positive rates for the two groups, A equals 0, A equals 1, and we'll let delta minus be the difference in the counterfactual false negative rates. The estimand then is the parameter theta star that minimizes the loss, subject to first making sure that theta is a vector of probabilities, and second, insisting that the error rate differences are no larger than these values epsilon plus and epsilon minus, which are chosen by the user. If you set epsilon plus and epsilon minus to both be 0, that means requiring that counterfactual equalized odds be satisfied exactly. As those values move towards 1, the fairness constraints get less and less stringent. If you set them both to 1, that's tantamount to imposing no fairness constraints at all. Since we have counterfactual quantities here, we need assumptions in order to identify those quantities in terms of observable data. So we make 3 standard causal inference assumptions. Consistency says that the outcome we observe for each individual is precisely the potential outcome corresponding to the treatment received. This assumes, for example, that people's treatments don't interfere with each other. The second assumption, positivity, says that the probability of receiving treatment conditional on the covariates is bounded away from 1. So there's still some randomness in treatment assignment conditional on these covariates. And the last assumption, ignorability, also known as no unmeasured confounding, is that the potential outcome is conditionally independent of the treatment decision given this same set of covariates. This means that there are no unobserved variables that affect both the potential outcome and the decision. So once we've conditioned on these covariates, the treatment is essentially random with respect to this outcome. So to get some intuition for when ignorability does and doesn't hold, here are 2 possible causal DAGs that could underlie the data. The key difference is that in the second one, we have unobserved variables v that affect both the decision and the outcome y, and this leads to a violation of ignorability. Note that we're not assuming the left DAG holds per se. This is just an illustration to provide some intuition about this assumption. So under these 3 assumptions, theta star can be written as the solution to a linear program whose coefficients are all identified. So on the left, we have theta star as it was defined above, and on the right, we have theta star as the solution to a linear program with coefficient vectors beta, beta plus, and beta minus. To construct an estimator, theta hat, we simply estimate beta, beta plus, and beta minus, and then solve the resulting estimated linear program. The interesting thing here is that the betas contain infinite dimensional nuisance parameters, which arise as a result of the counterfactuals that they contain. So we could simply use plug-in estimators for the betas, but in general, plugin estimators can't attain root-n rates in non-parametric settings. So instead, we propose using doubly robust influence function-based estimators, which attain faster rates than plugin estimators. Now, a natural question that arises is, how do the rates for these coefficients affect the performance of the resulting post-process predictor, S theta hat? It turns out that the rates for the linear program coefficients propagate in a certain sense to the post-process predictor. So if the coefficient estimators are consistent at some rate f of n, then the loss gap and the excess unfairness of S theta hat go to 0 at rate fn or root n, whichever is greater. By loss gap here, we mean loss beyond the loss of the optimal fair predictor, so this is close to the conventional notion of excess risk. And by excess unfairness, we mean any difference in false positive or false negative rates beyond the constraint epsilon plus, epsilon minus set by the user. In practice, before deploying a predictor, you need to know how it performs. So let's say you've constructed in step 1 here an estimate of the parameter theta star, call it theta hat. This indexes a particular post-process predictor S theta hat, and you then want to estimate the loss and fairness properties of that fixed S theta hat. Only if it looks reasonable would you actually want to deploy it. So this motivates our second set of estimands. These estimands are going to be well-defined for any fixed valid parameter value theta. But in practice, we're probably going to be most interested in the case where theta is equal to whatever we've estimated for theta star, so theta hat. First, we want to estimate the loss of our new post-process predictor, and then we want to estimate the loss change. For example, any reduction in accuracy that results from imposing the fairness constraints. Next, we want to estimate the error rate differences, for example, to see whether they're inside or outside those epsilon bounds that we set. And last, we want to estimate the proportion of input predictions that the post-process predictor flips as a way of understanding the impact of post-processing. Again, we propose doubly robust estimators for all these quantities. And note that if we set theta equal to this vector, 0, 1, 0, 1, we recover the input predictor. So we can also use these estimators to understand the behavior of the input predictor itself. Now, in order to estimate things well, we need to use separate samples, one to compute theta hat, and then another sample to compute properties of the resulting fixed post-process predictor, S theta hat. Again, there are a couple nuisance parameters that we have to estimate in order to get to the target parameters that we actually care about. I won't spend time describing these nuisance parameters, but the important point is that in order to get good statistical performance without imposing strong parametric assumptions, we need to further separate the estimation of the nuisance and target parameters. So within this sample D-train, we use part of the data to estimate the nuisance parameters and part of it to compute theta hat, and then we use a separate sample D-test in an analogous fashion to estimate properties of the fixed post-process predictor S theta hat. For simplicity here, we're showing a single split within each dataset, but the results hold if you use cross-fitting within each dataset instead, and that's what we'll actually do in practice. Now we turn to results. So there's no existing method designed to satisfy counterfactual equalized odds. So instead of comparing our method to another method like that, we compare results for doubly robust versus plugin estimators using simulated data. So here the x-axis represents samples of size 100 to 200,000, 20,000. The y-axis represents the loss in the left column or the excess unfairness values in the other two columns. Each vertical black line represents a mean plus or minus 1 standard deviation over 500 simulations. The horizontal orange lines represent the values for the optimal fair predictor. So in the top row, we see that the loss and excess unfairness converge to the values for the optimal fair predictor, as expected. In the bottom two rows, we see the results centered and scaled by root n. Here we can see that root n convergence is only achieved by the doubly robust estimator in the middle row. For the plugin estimator in the bottom row, the values begin to diverge in n. So the top row illustrates that the method works as intended, and the bottom two rows illustrate the advantages of the doubly robust estimators over plugin estimators in this problem. Next, we explore the performance fairness trade-off. So how does imposing fairness constraints affect the accuracy of the predictor? To examine this, we take as input the unconstrained Bayes optimal predictor with respect to y0. This is the best performing predictor we could start with. In our data generating process, this predictor has a loss of 0.24 and error rate differences of 0.23 and 0.4, which seem pretty unfair from the standpoint of equalized odds. This figure shows the increase in loss for the post-process predictor relative to the Bayes optimal unconstrained predictor as we range over a grid of values for epsilon plus and epsilon minus, which are those fairness constraints. The black region at the bottom left represents points where the fairness constraints we impose are looser than the fairness values of the input predictor. So as you would expect, our method just returns the input predictor and there's no change in performance. As soon as we start imposing fairness constraints that are tighter than these values at the edge of the black region, the loss starts to increase. As we move toward the top right corner, we're getting more and more stringent with the fairness constraints, and the loss increases accordingly, although not massively. So at the very top right cell, we've required exact counterfactual equalized odds. At this point, the loss increases by less than 0.1 over the unconstrained Bayes optimal input predictor. These types of results obviously depend on the data generating process, but they illustrate that it's possible in principle to satisfy fairness without taking a big hit in the performance of the predictor. Finally, we illustrate our method on the COMPASS dataset. As a note, this is meant to be illustrative of our method. Whether or not you believe these results substantively with respect to COMPASS per se depends on whether you think the assumptions, the causal inference assumptions, are satisfied in this context. So again, we split the sample so that the loss and the excess in fairness are estimated on separate data from the data used to construct the post-process predictor. We can see in the left column that the input predictor, which is a binarized version of COMPASS itself, has lost 0.36 and error rate gaps negative 0.24 and 0.18. These values reflect a result similar to what ProPublica found, namely defendants labeled Caucasian have higher false negative rates and lower false positive rates compared to defendants labeled African American. In the right column, we see that post-processing successfully controls those error rate differences to be within the target levels of 0.05, and it does so while incurring an increase in loss of just 0.03. In the bottom right cell, we see that this corresponds to flipping 9% of the COMPASS predictions. So how does post-processing accomplish this shrinking of error rates? This is the value of theta hat, and we can interpret it as follows. The 0 and the 1 mean that COMPASS scores are never flipped for either low-risk African-American defendants or high-risk Caucasian defendants. 0.91 means that 9%, 1 minus 0.91, of the scores for high-risk African-American defendants are flipped, and 0.23 means that 23% of scores for low-risk Caucasian defendants are flipped. And this makes some sense since COMPASS by itself was estimated to have disparities going in the other direction. So to summarize, we defined as an estimand an optimal, fair, post-process predictor S theta star that satisfies approximate counterfactual equalized odds, and we developed an estimator that's easy to compute and whose loss gaps and excess unfairness go to 0 at fast rates under appropriate assumptions. In ongoing work, we extend this method to the case where the input predictor is continuous or even missing, in which case we're in the in-processing setting rather than the post-processing setting. We're also extending this method to accommodate other fairness criteria, including observational criteria, which place the problem in a pure predictive setting rather than a risk assessment setting. Thank you very much, and I'm looking forward to questions and feedback.